Today we're going to cover Lesson 5 and Lesson 6. Lesson 5 is more about Taylor polynomials and Taylor series. Now it was important that last time we remember the power series for e to the x, sine of x, and cosine of x. We'll deal a little bit more with those today. So it's important that we have those power series because when we want to approximate something like sine of 1, for instance, in this first example, we don't have algebraic formulas that represent sine very accurately. So it's important that we have these polynomials in order to be able to approximate without using our calculator. Now, in class, I discussed that sine of 1 should be in between sine of 0 and sine of pi over 2, because 1 radian is in between 0 radians and pi over 2 radians. We discussed that sine of 1 is probably going to be closer to sine of pi over 2, so I should expect that my answer should be around 1, maybe a little bit less. Okay, it also asks us to make sure that the error in our approximation is less than 1 over 1,000. We'll deal with that in a second, because I will introduce a new formula. The first thing we should do is write down the power series for sine of x. So the power series for sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and it keeps going. Remember that power series are the sum of an infinite number of terms. Now, if I want to approximate sine of 1, I need to plug in 1 for x. So that's pretty easy. I plug in 1, and 1 cubed is 1 over 3 factorial, plus 1 to the 5th is 1 over 5 factorial, minus 1 over 7 factorial, and so on. Okay. Now, I could sum up an infinite number of terms, and my approximation would be almost exact. But they're allowing us to have some kind of error in here. I want my error to be less than 1 over 1,000. So there are 3 conditions that we must establish before we are allowed to use a certain formula for the error, or a certain formula to restrict the error. So the first thing I have to verify, and maybe I'll make a little table over here, first is that the series is alternating. That means that it alternates between plus or minus signs. Yes, the series is alternating. The second thing that we must verify is that the series is decreasing in magnitude. Each term is getting smaller. Decreasing in magnitude. The third thing that we must verify is that the limit of the terms goes to 0. If we can say all of these things about the series, then it is given that our error, the error of our approximation, will be less than the absolute value of the first neglected term. And you're like, what is that? Finish this. Neglected term. Oh, sorry. Well, the first neglected term is the first term in our series that is relatively insignificant. So if I don't know the value of each of these factorials, maybe I should write them out to figure out which of these is relatively small. So if I'm writing out factorials, I have that sine of 1 is equal to 1 minus 1 over 6 plus 1 over 120 minus 1 over 50, 40, and so on and so forth. This term, right here, is very small. 1 divided by 5,040 is a very small term, almost insignificant in our sum. So, I also noticed that 1 over 5,040 is less than this error term. Remember that they want our error to be bounded by 1 over 1,000. So if I can say that the first neglected term, which is this one, will be this one in our sequence, is less than this, I can say that my error will also be less than this. Okay? So I'm looking for, in order to find that neglected term, I am looking for the first term here that is less than the error that they're asking me for, right there. Okay? So for my approximation, I kind of stop it right there. I say this is the term I'm going to neglect, this will be the upper bound for my error. If I finish out this approximation, let me use a little space down here. I get that sine of 1 is approximately, now 1 minus 1 over 6 plus 1 over 120. And getting a common denominator, I get that this is equal to 101 over 120. So my approximation for sine of 1 is 101 over 120. And that makes sense in context, because remember we thought about how it should be between 0 and 1, but a little bit closer to 1. Okay. Since I know these three things about my series, then I know that my error is bounded by the first neglected term. Again, that is this term right here, first neglected term. So I know that this will be less than negative 1 over 50, 40, which is, of course, less than 1 over 1,000. That's me just finding that my error is less than 1 over 1,000. If it's bounded by this term right here, then it must be less than this. Okay? I can only use this if I establish these three conditions. Well, I ran out of room a little bit here, so let me scroll down a little bit. Now, right here in part B, it said, use your calculator to find the actual error. Okay? If I do that over here, I find that my error, remember the error is equal to the absolute value of the actual value, so sine of 1, minus your approximation, which is 101 divided by 120. If we put this in our calculator, we get that our error is equal to 0.000195, which definitely is less than 1 over 1,000. So it's important that we establish these three conditions to be able to justify that our error is less than 1 over 1,000. All right, so in the second example, we scroll down a little bit. I want to find a series that represents the antiderivative for sine of x squared, and then I will use it to approximate this integral. So the first thing I should do is, let me scroll down a little bit more, give a little more room, find that series. So I know the series for sine of x. Let's write that again. So the series for sine of x, again, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. Now, if I want to find it for sine of x squared, I need to make that substitution. So sine of x squared is equal to x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, and so on. This is my series, my power series for sine of x squared. And it wants me to take the antiderivative of this. So antiderivative, I am integrating sine of x squared with respect to x. So I'm integrating this series right here, and I am getting x cubed over 3 minus x to the 7th divided by 7 times 3 factorial plus x to the 11th divided by 11 times 5 factorial minus x to the 15th divided by 15 times 7 factorial, and so on. So this right here is the series approximation for the antiderivative of sine of x squared. That was the answer to the first question. Then they asked us to use this to approximate the series, use it to approximate the integral of sine of x squared from 0 to 1. We have to approximate this because we can't integrate sine of x squared. We don't know the method. So we need to use our approximation. And again, they want my error to be less than 1 over 1,000. All right, so the only thing I need to do is make this a definite integral. So I want to integrate from 0 to 1 sine of x squared x. And then it's just me evaluating this integral, or this, series from 0 to 1. cubed over 3 minus x to the 7th over 7 times 3 factorial plus x to the 11th divided by 11 times 5 factorial minus x to the 15th divided by 15 times 7 factorial, and so on, evaluated from 0 to 1. Now all the 0 terms will go away, but I need to evaluate the terms with 1. So the first one will be 1/3 minus 1 over, remember 3 is 6, or excuse me, 3 factorial is 6, so this is 1 over 42. Then, excuse me, 1 divided by an 11 times, and 5 factorial is 120. Minus 1 over 15 times 7 factorial, and so on and so forth. Now remember that I want my approximation, if I scroll up a little bit, I want my approximation to have an error less than 1 over 1,000. And to do that, I need to figure out which term will be less than 1 over 1,000. If you look right here, this term, this denominator, is going to be greater than 1,000. So remember that if my error, if the series is, excuse me, let's verify our terms, if the series is alternating, decreasing in magnitude, and the limit of the terms goes to 0, then the error will be less than the first neglected term. So I'm looking for the first neglected term that is also less than 1 over 1,000, because that is what I want my error to be less than. If we look here, it is this term. So I'm going to cut off my approximation right there. All right, if I continue with my approximation, I write a little approximate sign. It is 1/3 minus 1 over 42, which is 13 over 42. That is my approximation for the integral of sine of x squared from 0 to 1. Now I need to say that my error, since all of those conditions that I established to the left are true, my error will be less than 1 over 11 times 120, okay? Which inherently is less than 1 over 1,000. Okay? So we have both found the approximation for an integral, and we have justified that the error is less than 1 over 1,000. If we go to the next page, you'll notice that it wants you to check the actual error. And remember, I need to plug this into my calculator, and I will find that the error is equal to 0.000744. And that is definitely less than 1 over 1,000. And if you check, this will be less than 1 over 11 times 120. Notice that that was the first neglected term, so it should be greater than my error. The final example, it's asking you first to write the Maclaurin series for e to the x. So let's review. The Maclaurin series for e to the x is 1 plus x squared plus x cubed. I'm supposed to give 4 non-zero terms and the general term. So don't forget your 3 dots. The general term is x to the n. It continues on an infinite number of terms. So that is a power series for e to the x. Then I need to use this to find this limit. So since f of x is e to the x, f of x is e to the x, I will use my power series in this limit. So let's make a substitution. My limit as x goes to 0. And here I am subbing in my power series. So I'll do the first 4 terms. I'll do 1 plus x squared plus x cubed, my 3 dots. Okay? And I have minus 1 divided by 2x. If I want to simplify this limit, the first thing I should notice is that this 1 and this 1 cancel out. There's opposite, they subtract. Then I want to divide the 2x into each term. each term. Okay? So if I do that, the limit as x approaches 0, don't forget good limit notation. Make sure that you're continually writing limit as we go along. And x divided by 2x is 1/2. And the next one, x squared divided by 2x. Oh, you know what I just realized I forgot? I forgot all of my factorials. Let's go back and write them. This is such an easy mistake. Factorial, 3 factorial, n factorial. My apologies. Let me go ahead and fix this. As my first period would say, what a rookie mistake. That's okay. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, so now we're ready. All right, the ones still go away, still subtract out, and x divided by 2x is still 1/2. The next term will be x squared divided by 2 factorial divided by 2x, so I will get plus x divided by 2 times 2 factorial. The next term, I will get x squared divided by 2 times 3 factorial. Okay, maybe divided by one more term, I will get x cubed divided by 2 times 4 factorial, and so on and so forth. Now when I evaluate the limit by plugging in x equals 0, all of these terms and all of the other terms will go to 0, and I will be left with just 1/2. And that's my final answer. There is a secondary way to do it, though. Notice, think back to chapter 3 or 4, maybe, when we started with derivatives. And let me write e to the x instead of f of x this time. So just subbing in that e to the x. If I plug in 0, I get the indeterminate form 0 over 0. 0 over 0 is indeterminate. So I can use L'Hopital's rule. If I use L'Hopital's rule, then I will be taking the derivative of each. So I have the limit as x goes to 0 of e to the x, the derivative of the top divided by the derivative of the bottom. Plugging in 0, I get 1/2. So the same answer as I got before. All right, so there you have it. That is lesson number 5. Okay. All right, this is the worksheet, the second worksheet for that lesson. And here we go. Oh, sorry, that's one more problem. Lesson number 6. Lesson number 6 is about the Taylor series and Taylor polynomial for geometric series. Now, back in Algebra 2, you should have learned that a geometric series is one where the difference between the two terms is a common ratio r. So, for example, let's do these 3 examples. If I start with a equals 2 and r equals 3, if I was to write this in summation notation, this would be the sum n equals 0 to infinity of 2 times 3 to the n. If I was to write this as a series, we start with n equals 0. So at n equals 0, the first term is 2. Then I multiply by 3 to get the next term. So my next term is 6. Again, multiplying by 3, I get 18. And then 54. Okay, and my general term is exactly what is written right here. My general term is 2 times 3 to the n. Couple dots at the end. Okay, but what if I change r to -3? Then I get, change colors here, my first term will still be 2, because a is still 2. Then my next term will be -6. The following term will be positive 18 again, and then -54. So you can write the general term in 2 different ways. You could write it as 2 times -3 to the n, with continuing on after that, or you could write it as 2 times -1 to the n times 3 to the n. This is why we get that, this is that alternating sign that we saw in both sine and cosine power series. This is because we notice we have a minus, a plus, a minus, a plus, and so on and so forth. Finally, if we do this last example, A is 1. That means the first term in the sequence is, in the series is 1. And everything else I multiply by x. So 1, the next term is x, then the next term is x squared, the next term is x to the third, the general term is x to the n. Notice that these don't have factorials. So geometric series do not have factorials. I'm not dividing by anything. And that's because I am forming the series by multiplying the prior term by some ratio r. So I notice that in order to get from 1 to x, multiply by x. And in order to get from x to x squared, multiply by x. And the same for every single term in the sequence. Before, in Algebra 2, we were told that the sum of an infinite series, so this right here, sum of an infinite series, let me move this up a little bit, can be found by using this formula. And hopefully that rings a couple bells. If not, maybe you've seen that formula before. It does appear on the SAT. So, sum of an infinite geometric series is equal to A divided by 1 minus R, where A is that first term and R is that common ratio. What we are going to do in BC is treat this sum of an infinite series, we're going to treat this as a rational function and ask you to write us a series for it. So kind of going the other direction that you did in Algebra 2 or before. Now something that we did, maybe I'll scroll down here to the bottom. If you have a scratch piece of paper, this would be a great place to put it. On the first day of class, we came in and we said, let's write 1 divided by 1 minus x. Let's write that as a series. And so the thing we did long division. We said, all right, 1 divided by 1 minus x. Okay, the first term is 1, so I get 1 minus x. I subtract, and I'm left with x. Okay, well, I can multiply by x and say 1 minus x squared. Subtract those, and I get x squared. And continuing on and on, adding x squared, x cubed, forever. But now, what if we treated this just like we treat the sum of an infinite series, that formula which is A divided by 1 minus R? Well, then we could say that A in this formula, if we're looking at this, A is equal to 1 and R is equal to x. If we then use these two things as the geometric formulas we did before, then 1 divided by 1 minus x would be equal to, the first term is always A, so 1, and I multiply by x, so x squared, x cubed, and so on and so forth. You'll notice that the long division gave us the same thing as writing it as a geometric series. So these definitely are equivalent. Two different ways of thinking about it. I can either think about it as a division problem, or I can think about it as the sum of an infinite series. And so this is what we're going to ask you to do. We're going to ask you to analyze functions like this and turn them into series like this. So let's go ahead and take a look. Oh, I forgot one more thing. Earlier in Chapter 9, we talked a little bit about convergence. Convergence is where the two functions are closest together, and whereas our approximation is the most accurate. And this will happen for a geometric series if r, the common ratio, the absolute value of r is less than 1. This is where it will converge. If the common ratio is outside of 1, is greater than 1, then it will diverge. Important to note, we will get there, we'll see this in the first example. Oh, it looks like I wrote a little too close. Let me erase some of this. Okay. Alright, so I see that they want us to find a power series for 1 divided by 1 minus x squared. If I treat this as the sum of an infinite series, then I can say that A is equal to 1 and R is equal to x squared. In writing a geometric series then, my first term is 1, the next term is x squared, and then x to the fourth, and then x to the 6th, and so on and so forth. That means our general term will be x to the 2n. And you can write that as x squared to the n or x to the 2n, whichever way you like it. So this is the power series. And let's check, is it centered at 0? Yes. Remember, centers are when when a power series is centered at something other than 0, we would have seen an x minus, let's say, 2, instead of just the way it is right now, where we don't see any additional constants in there. Okay. We gave the first 4 non-zero terms and the general term. For what values of x does my series converge? The series converges, remember, when the absolute value of r is less than 1. So r in this case was x squared. So I'm saying the absolute value of x squared will be less than 1. I want to solve for some more specific x values. This will happen if we think about it between -1 and 1. Remember when you were solving for absolute values in Algebra 2 or maybe Algebra 1, you had to make 2 different cases, a positive case and a negative case. I said that backwards, but a positive case and a negative case. The same applies here. We are looking to solve for x values and give ourselves kind of a window. Remember that little window that we talked about of convergence? This is it. This is our interval of convergence. So let's do another example together. This one's a little bit more tricky. Oh, excuse me. This right here, if you check on your calculator, graph the function in y1 and the first 5 terms of the series, you'll notice that there are asymptotes at when x equals -1 and x equals 1, and it will only converge in between. Okay. So check that out on your calculator if you've got a second. The next example looks a little different. Remember that our formula for the sum of the geometric series is that a divided by 1 minus r. Well, this formula right here does not have a 1, does not have a negative, so we're not really sure if this is we can't really take this information as written in order to form our geometric series. We have to do a little bit of manipulation. So if I write down 12 divided by 4 plus x, I really want to get rid of this 4. I want to make it a 1. When we think back to what we did for for arcsine and arctangent when we were doing those integrals, we can take out the 4. We can factor it out. So if I factor out the 4, I'm left with 1 plus x divided by 4. Then I can divide the 4 and the 12. So I will get 3 divided by 1 plus x over 4. Right? But we're still missing this negative right here. But this is easy enough to solve. I can write plus x over 4 as minus negative x over 4. Kind of the opposite of everything your algebra teacher taught you. Write it back as minus a minus. Okay? Now, this formula matches sum of infinite series. So I can use this information to write the series. All right? If I use this, I notice that a is equal to 3, and r is equal to negative x divided by 4. Now we're ready. So I can say that 12 divided by 4 plus x is equal to the power series 3 minus 3x over 4 plus 3x squared divided by 16. Remember, I'm multiplying by negative x over 4 every time. Okay? Minus 3x cubed over, oh, I'm sorry. Oh, it seems to have lots of page. Over 64, not 54. My apologies. Okay, and the general term, it has alternating signs, so I know I will need a -1 to the n. The 3 is always there, so I'm going to write the 3. I also have x to the n and divided by 4 to the n. You can combine these 3 terms because they're all to the same power, or I could have written this as 3 times negative x to the n divided by 4 to the n. That's okay, as long as they're the same kind of exponent, being raised to the same powers. Okay, so that is the infinite series. And then it asks us for what values of x does our series converge. So again, we are looking for when an absolute value of r, so the absolute value of negative x divided by 4 is less than 1. Now in solving this, I want to get rid of the absolute value by establishing two cases. Okay. And if I multiply everything by negative 4, I have to change all the signs and flip the inequalities. So I will get 4 greater than x greater than negative 4. And we really don't like to write it that way, so I would prefer it if you wrote it as negative 4 is less than x is less than 4. And this is our interval of convergence. Something you should start thinking about is that the fact that our series is centered at 0. So by looking at that center right in the middle here, we can tell that the radius of convergence is 4. 4 this way and 4 this way from our center. All right, last example. Another manipulation trick. I have a power series, and let's 5 divided by 4 minus x. This isn't too different than the one we did last time, but I now want to be centered at 3. So remember, when Taylor polynomials are centered at 3, we have something that looks like x minus 3 plus x minus 3 squared over 2 factorial plus x minus 3 cubed over 3 factorial, maybe without the factorials. But notice that the power on x minus 3 increases by 1 every time. It's like you're multiplying each prior term by x minus 3. You're multiplying each term by x minus 3 to get to the next one. So if we think about it that way, we want an r, our r of our geometric series, to be x minus 3. We want to multiply each term by x minus 3 to get to the next term. Okay? Well, I don't know if I have that yet, but I can use this 4 to manipulate it to get an x minus 3 as my r. Notice that I can write 4 as 1 plus 3 minus x. Now if I use the associative property, and group those two together, now I need to be in the reverse order with different signs, so I can take out a negative, and I will get 5 divided by 1 minus x plus, x minus 3. X minus 3. Now, if we compare that to our sum of infinite series, I both have a negative here, and I have a 1 right here. So this is all the information I need to write my infinite geometric series, with a equal to 5 and r equal to x minus 3. Okay, so if I look at it that way, give myself a little bit more room, then I'm ready. I have that 5 divided by 4 minus x is equal to 5 plus 5 times x minus 3 plus 5 times x minus 3 squared plus 5 times x minus 3 cubed. Okay, and then we move down here to write my general term. 5 times x minus 3 to the end. Okay, and since I have this x minus 3, I can tell that my power series is centered at 3. I also need to reflect back, look, and to see where the series converges. Again, the series converges when r, the absolute value of r, is less than 1. And that is when x minus 3, absolute value, is less than 1. To solve, I get two cases, negative 1, x minus 3, and 1. Then I add 3 to both sides to get 2 is less than x, less than 4. Now I think to myself, does this make sense? Is this an okay interval of convergence? And I look back, what context clues do I have? Well, yes, the center should be right in the middle, and the center is 3. So yes, my center is in the middle here, and my radius of convergence is 1 on both sides, which makes sense. And that is writing geometric series.